Welcome everyone to our video on Lewis structures. In this video, we are going to look at how to build Lewis structures for small molecules given the molecular formula. This video is going to expand on some of the ideas that we were introduced to in earlier grades about drawing molecular structures using the Lewis theory of covalent bonding. The reason we need to address drawing Lewis structures again is that it turns out that the Lewis theory has some limitations. Now recall that the Lewis theory of covalent bonding states that atoms each contribute one unpaired electron to form a covalent bond, and that atoms combine in a way so that all atoms in the molecule will reach a noble gas electron configuration. Now, these two statements are a bit of a problem because the Lewis theory cannot account for countless observed molecular structures. Great example are carbon-based molecules, and that's a huge problem for organic chemistry. Carbon only has two unpaired valence electrons. So in theory, carbon should only be able to form two bonds, but that doesn't get it to an octet. And we know that carbon forms four bonds to reach that octet. So the Lewis theory, as it's stated, doesn't quite explain for carbon-based molecules. There are also some molecules that you may not have encountered before, such as xenon hexafluoride, and there we have a noble gas forming bonds. So how is it that a noble gas, which already has a noble gas configuration, is forming a stable molecule? So these are just two of many examples about why we need to make some adjustments to the Lewis theory in order to account for these. We are going to make two primary adjustments to our method for creating Lewis structures. The first is that we will no longer require that each atom contributes one electron to form that covalent bond. Rather, we are going to look at the total number of valence electrons that are available from all the atoms forming bonds and deal with those together, kind of like a pool of available valence electrons that we can form bonds as we wish from those. The second one is that even though the octet or the noble gas electron configuration will still be the norm, it's not going to be necessary. We'll come across examples of an octet deficient molecule, and we'll also have examples of expanded octets. The way we're going to approach this is that we're going to go through a series of steps on how we're going to build Lewis structures. Think of it almost as an algorithm. As we're going through the steps, I'm going to explain some of the reasoning behind the steps, but we'll also get a more detailed understanding of the reasoning as we get into orbital bonding theory and then look at VSEPR theory as well. So for right now, view them as a series of steps that are going to work well to get to the likely Lewis structure. Let's now switch over to the whiteboard and go through some examples on building Lewis structures. For our first example here, we're going to look at drawing a Lewis structure for PCl5, phosphorus pentachloride. Our first step is to determine which atom is going to be the central atom. Now, the central atom needs to share more electrons. So we're going to choose the atom that has the highest bonding capacity, or the atom that is the least electronegative. And I say or because those are often the same element. Remember that halogens and hydrogen can only form one bond, so they're almost never the central atom. Phosphorus has the lower electronegativity, so it's going to be the central atom, and we're going to place the other chlorines around that central atom. In this molecule, we refer to the chlorines as the terminal atoms. Our next step is to determine the total number of valence electrons. The phosphorus atom has 5 valence electrons. Each chlorine atom has 7, and we have 5 chlorine atoms. So in total, we have 40 valence electrons. Now we're going to start distributing those 40 valence electrons between the bonds and the individual atoms. Our third step is to form bonds between the terminal atoms and the central atom. Remember that each line represents 2 bonding electrons, or a bonding pair. So far, we've used 2, 4, 6, 8, 10 of our valence electrons. Our next step is to complete the octets, if possible, of the terminal atoms. So we have 5 bonds formed for a total of 10 electrons. Starting in 3, 2. Our next step is to complete the octets, if possible, of the terminal atoms. We've already used up 10 of our valence electrons, so that means we have 30 more that we need to use. So as we're going here, we're going to place them in pairs. So the chlorine, 2, 4, 6, 8 from the bonding pair, so there's the octet for the chlorine. As we're going here, count to make sure that we don't run out of valence electrons. So we've used 10, 12, 14, 16. And that brings us to 40 valence electrons. So for this molecule, we've used up all of our valence electrons, completing the octets of the terminal atoms. Our next step would be to place any leftover valence electrons on the central atom. Now, we don't have any left over, so we are not going to do anything there. But I should note that here we have an expanded octet. So phosphorus has a total of 10 electrons between these 5 bonded pairs. This will be allowed for elements in the 3rd period and lower, okay? So if our central atom is in the 1st period or the 2nd period, it cannot expand its octet, only in the 3rd, 4th, and so on periods. The other possibility would be that our central atom still didn't reach an octet. If that was the case, we take a lone pair from one of our terminal atoms and turn it into a bonded pair. We'll see examples like that as we do more practice. Let's now look at the second example. For our second example, we have a polyatomic ion, IF4 1+. Now here we have 2 different halogens, iodine and fluorine. They can each, in theory, form 1 bond to reach the octet, but we know that some elements can expand the octet. That is why iodine is going to be our central atom. Iodine is found in the 3rd period or lower, so that means that it can expand its octet. It also has a lower electronegativity than fluorine, which matches up with how we were going to select our central atom. So our first step is complete. We have our central atom with our 4 terminal atoms distributed around that central atom. Now let's count the total number of valence electrons. We have 1 iodine, which has 7 valence electrons, and 4 fluorines, which also has 7. But this has a charge of 1+, so this molecule has lost one of those valence electrons, so we're going to subtract 1 from the total. So we have a total of 34 valence electrons. Our next step is to form a single covalent bond between the central atom and the terminal atoms. This creates our molecule. And now we're going to complete the octet on the terminal atoms. Let's count the valence electrons that we've used now. In the bonded pairs, 2, 4, 6, 8. And then we have 4 fluorines, each with 6 lone electrons. So that's 24 plus 8. So we've used 32 of our valence electrons. So that means we still have 2 left over. So our next step will be to place any remaining electrons on the central atom. Once again, iodine is in period 3 or lower, so that's okay for it to expand its octet. So now we've used all the valence electrons and we've completed the Lewis structure. Now this is a charged ion, so we often represent charged ions with square brackets and put the charge outside like this. Let's now review our steps for creating these Lewis diagrams. Our first step was to select the central atom and arrange the other atoms, the terminal atoms, around that central atom. Recall that the central atom was the one that's the least electronegative. Hydrogen halogens are usually terminal atoms. Next, we calculated the total number of valence electrons between all of the atoms in the molecule or polyatomic ion. Recall that if it's an ion, we either have to add or subtract electrons. Then we created a molecule by forming a bonding pair between each terminal atom and the central atom. Our next step was to complete the octet of the terminal atoms first. Recall that if it's hydrogen, hydrogen only needs 2 electrons to reach that noble gas configuration. We paired those electrons up, counting as we go. And then once we've completed those octets, if we had any electrons left over, we place them on the central atom. And that if that central atom is in the 3rd period, 4th period, 5th period, and so on, you can exceed the octet. If our central atom still doesn't have an octet, we will take a lone pair from a terminal atom and to form double or triple bonds if necessary in order to reach an octet on the central atom. This step often confuses people that we're moving electrons around. One thing to remember is that these steps for building Lewis structures, it's not actually how a molecule forms. It's an algorithm on paper that's going to result in the most likely Lewis structure. Remember that when you move a lone pair of electrons to a bonding pair, that terminal atom does not lose its electrons. It's just now sharing 2 electrons that we had assigned to it all by itself initially. So these are the steps here that we will follow in general to reach the most likely Lewis structure.